Welcome all, I am Maria Vincent, Assistant Professor, Department of Electronics and Communication Engineering, Rajagiri School of Engineering and Technology. Today I will be going to discuss on the topic frequency modulation, which comes under the course Electronics Communication for S7 EE students. So before going to detail the concept frequency modulation, first of all we want to consider the angle modulation. So the angle modulation occur whenever the phase angle of a sinusoidal wave is varied with respect to time. So as same as that of amplitude modulation, in case of angle modulation also the carrier signal is always sinusoidal signal, and that carrier signal is given as EC of t is equal to EC into cos 2 pi FCT plus 5C, where EC represents the peak carrier amplitude in volt and FC represents the frequency of the carrier signal and 5C represents the phase of the carrier. So the term 2 pi FCT plus 5C represents the angle of the signal. So the frequency or phase can be varied using a modulating signal. Whenever the frequency or phase changes, the angle of the carrier also changes. So the term 2 pi FCT plus 5C represents the angle of the carrier signal. So if we are changing the frequency or the phase, then the angle of the carrier also changes. Hence it is called as angle modulation. So whenever the frequency phase changes, the angle of the carrier also changes. Hence it is called the angle modulation. Now we'll discuss frequency modulation or FM. So the FM is defined as the process by which the frequency of the carrier is varied according to the message signal. So the instantaneous frequency after the frequency modulation is given by Fi is equal to Fc plus Kf into m of t. So this Kf into m of t represents the modulating signal and Fc represents the carrier frequency, where Kf is the frequency sensitivity of the modulator, which is in terms of hertz per volt, and this Kf indicated the change in carrier frequency for 1 volt change in the message signal. So this Kf represents the frequency sensitivity, which indicate the change in the carrier frequency for 1 volt change in the message signal. And the instantaneous frequency after the frequency modulation Fi is equal to Fc plus delta F. So Fc represents the carrier frequency and delta F represents the frequency deviation experienced by the FM signal. So Fi is equal to Fc plus Kf into m of t, which can be rewrite as Fc plus delta F, where delta F is the frequency deviation which is given as Kf into m of t. So where Kf represents the frequency sensitivity of the modulator. So the frequency deviation is the change in frequency that occur in the carrier when it is acted on by a modulating signal frequency. And in case of frequency modulation, which is an analog modulation technique, both the message signal as well as the carrier signal is a sinusoidal signal, or we can say a time varying signal. So for a message signal, m of t is equal to Em into cos 2 pi Fm into t, where Em represents the amplitude of the modulating signal, Fm represents the frequency of the modulating signal, and t represents the time varying signal. So the maximum frequency deviation delta f is given as kf into m of t the whole max, which is equal to kf into em. So the maximum deviation from the carrier center frequency will be by an amount equal to the frequency deviation. So the maximum deviation is equal to kf into em. So em represents the maximum swing or the amplitude of the modulating signal. So delta f is equal to kf into em, which represents the maximum deviation from carrier center frequency. So this waveform explained the FM waveform. So the first signal represents the high frequencies carrier signal, and the second one represents the modulating signal, and the third one represents the FM modulated signal. So with no modulation or with a no modulating signal, the FM modulated wave is simply as same as that of the carrier signal. So with applying the modulating signal, the frequency of the carrier signal starts varying in proportion with the modulating signal. So in this figure you can see that the maximum frequency deviation, that is the change in the carrier frequency, occurs during the positive and the negative peak of the modulating signal. So during the positive half cycle of your modulating signal, you can experience the change in the frequency, and during the negative half cycle, the frequency there occur a frequency change, that is the frequency deviation is proportional to the amplitude of the modulating signal. So the rate at which the frequency changes is equal to the modulating signal frequency. So now we can derive the expression for angle modulated signal. An angle modulated carrier signal is given by S of t is equal to EC into cos theta of t, where theta of t represents the 2 pi fct plus 5c. So the instantaneous frequency Fi is equal to 1 divided by 2 pi into d by dt of theta of t. Now we can write theta of t with respect to Fi, which is given as theta of t is equal to 2 pi integral Fi into dt. So from this relation we can write the expression for theta of t, which is equal to 2 pi integral Fi into dt. So this theta of t is equal to 2 pi integral, where Fi is equal to Fc plus Kf into m of t, which we already seen in the first two slides. So theta of t is equal to 2 pi integral Fc plus Kf into m of t into dt. In this equation, both the Fc and Kf are constant. So we can take this Fc and Kf outside from this square bracket. So this theta of t is become 2 pi Fct plus 2 pi Kf integral m of t into dt. So this m of t is changing with respect to t, that is why it is integral m of t into dt. So theta of t is now become 2 pi Fct plus 2 pi Kf integral m of t into dt. The angle modulated carrier signal is given by S of t is equal to Ec into cos theta of t. So in the previous slide we derived the expression for theta of t, which is equal to 2 pi Fct plus 2 pi Kf into integral m of t into dt. So if you substitute the theta of t in this equation, the angle modulated carrier signal is now become Ec into cos 2 pi Fct plus 2 pi Kf integral m of t into dt. So where this m of t is what? Our message signal, which is given as Em into cos 2 pi Fm into t. So now we can substitute this m of t in this equation. So the angle modulated wave now become S of t is equal to Ec into cos 2 pi Fct plus 2 pi Kf integral Em into cos 2 pi Fm into t. So now we can integrate this term. So the equation is now become Ec into cos 2 pi Fct plus, so in this equation Em is constant, so we can take 2 pi Kf into Em integral cos 2 pi Fm into t dt. So integral cos 2 pi Fm into t dt is now become sin 2 pi Fm into t divided by 2 pi Fm. So this term is become 2 pi Kf into Em divided by 2 pi Fm into sin 2 pi Fm into t. So this 2 pi and this 2 pi got cancelled. So now the equation has become Ec cos 2 pi Fct plus Kf into Em into sin 2 pi Fm into t. So now the equation has become S of t is equal to Ec into cos 2 pi Fct plus Kf into Em divided by Fm into sin 2 pi Fm into t. So this is the Fm modulated wave. Now for an ease of analysis, we can define the modulation index beta. So beta represents the frequency change. So this beta is equal to Kf into Em divided by Fm. So this term represents the modulation index. So for Fm, the modulation index is termed as beta. So the equation has become S of t is equal to Ec into cos 2 pi Fct plus beta into sin 2 pi Fm into t. So where beta represents the modulation index of Fm. So where this modulation index is equal to delta F by Fm. So where delta F is the frequency deviation which is equal to Kf into Em divided by the maximum message signal frequency. So in Fm, the spectrum of the modulated signal depends on the modulation index beta. So the demodulation technique remains the same independent of the value of the modulation index. Based on the modulation index, the frequency modulation can be classified as two, that is narrow band FM and wide band FM. So when the modulation index beta is less than 1, then that frequency modulation is known as narrow band FM, and when the beta is greater than 1, then it is known as the wide band FM. So now we can derive the expression for narrow band FM. So already in the previous slide, the frequency modulated wave can be mathematically represented as Ec into cos 2 pi Fct plus beta into sin 2 pi Fm into t. So for an ease of analysis, now we can make use of a trigonometric formula, that is cos A plus B. So cos A plus B is equal to cos A into cos B minus sin A into sin B. So here cos A plus B, where A is equal to 2 pi Fct and B is equal to beta into sin 2 pi Fm into t. So the cos of 2 pi Fct plus beta into sin 2 pi Fm t can be written with the help of a trigonometric formula, that is cos A plus B, which is equal to Ec into cos 2 pi Fct into cos of beta into sin 2 pi Fm into t minus the sin 2 pi Fct into sin of 2 beta into sin 2 pi Fm into t. Let beta into sine 2 pi fm into t, this term is theta. Here for an ease of analysis, the theta is less than 1, hence the cos theta can be approximate to 1 and sin theta can be approximate to theta. So the s of t can be written as EC into cos 2 pi fct into cos of beta into sin 2 pi fm into t minus sin 2 pi fct into sin of beta into sin 2 pi fm into t. So in this equation we make the cos theta approximated as 1, that is this term is now become 1. So this in this equation now it has become EC into cos 2 pi fct. Now the sin theta can be approximated as theta, that is the sin of beta into sin 2 pi fm into t now become beta into sin 2 pi fm into t. So the equation has now become EC into cos 2 pi fct minus EC into beta into sin 2 pi fct into sin 2 pi fm into t. So now we can substitute one more trigonometric formula, that is sin A into sin B. So sin A into sin B is equal to cos A plus B by 2 minus cos A minus B by 2. So now the narrow band FM signal can be written as EC into cos 2 pi fct plus EC into beta by 2 into cos 2 pi fc plus fm into t minus EC into beta cos 2 pi fc minus fm into t the whole divided by 2. So this wave represents the narrow band FM. So if you know the FM waveform, then we can easily draw the frequency spectrum. So in this expression, this EC cos 2 pi fct represents the carrier signal with an amplitude EC with a frequency fc. So at fc we are having an amplitude of EC. So as same as that of AM, in this FM we are having an upper sideband signal and a lower sideband signal. So the upper sideband signal, which is at a frequency fc plus fm with an amplitude of beta into EC by 2, and the lower sideband frequency, that is fc minus fm with an amplitude of minus EC into beta by 2. So minus represents what? At the negative, that is minus beta into EC by 2. So from fc to fc plus fm it represents the upper sideband frequency, and from fc to fc minus fm it represents the lower sideband frequency. Now we can write the expression for bandwidth, which is the higher frequency minus lower frequency. So from this spectrum, the higher frequency is fc plus fm and the lower frequency is fc minus fm. So the bandwidth is equal to fc plus fm minus fc minus fm, which is equal to 2 times fm, that is the 2 times the modulating frequency. So the bandwidth of an FM signal is given by 2 times FM, which is same as that of bandwidth of an AM signal. So for both the AM as well as for the narrow band FM, the bandwidth is given as 2 times the modulating signal frequency. Now we can derive the expression for average power for narrow band FM. So in the previous slide we derived the expression for the narrow band FM, and from the narrow band FM we drawn the frequency spectrum. So the magnitude spectrum of the narrow band FM signal is same as that of the spectrum of an AM signal. So it is understood that both the AM as well as for the narrowband FM, it contains 3 signal components, that is a carrier component, then upper sideband and the lower sideband. So the bandwidth and the power remains the same. So the bandwidth is equal to 2 times FM and the total transmitted power is become PC into, that is the carrier power into 1 plus beta square divided by 2. So the same derivation of AM can be used here, and the final the total transmitted power now become carrier power into 1 plus beta square by 2. So in case of FM, the modulation index is given as beta. So in practical application, the narrowband FM is not used due to its similarity with FM. So both the bandwidth as well as the total transmitted power is same as that of FM. So therefore we go for the wideband FM, which is also known as WBFM, which has wide range of applications in radio and audio processing in TV. So now we can consider the wideband FM, where the modulation index beta is greater than 1. So in order to derive the expression for the wideband FM, here also first of all we want to consider the standard expression for FM signal, which is given as EC into cos 2 pi FCT plus beta into sin 2 pi FM into T. Since beta is greater than 1, the approximation cos theta is equal to 1 and sin theta is equal to theta is not valid. So in that case we have to make use of a Bessel function, which are used to solve the equation to determine the spectrum, and this Bessel function is given by Jn of x is equal to 1 by 2 pi into integral minus pi to pi e raised to j of x into sin theta minus n into sin theta of d theta. And this Bessel function is having two main properties, that is Jn of x is equal to minus 1 raised to n into j of minus n of x, and summation from n is equal to minus infinity to infinity j square n of x is equal to 1. So the time domain equation for wideband FM signal can be rewrite with the help of the Bessel function as EC into summation from n is equal to minus infinity to infinity j n of beta into cos 2 pi fc plus n into fm into t. So now we can write this equation for different value of n. So for n is equal to 0, this expression is become EC into j0 of beta into cos 2 pi fct. Similarly, we can write we can expand this expression for n is equal to minus infinity to infinity. So now it is written for n is equal to 1, that is EC into j1 of beta into cos 2 pi fc plus fm into t plus EC into j minus 1 of beta into cos 2 pi fc minus fm into t plus EC into j2 of beta into cos 2 pi f of fc plus 2 pi fm into t plus EC into j2 of beta into cos 2 pi fc minus 2 fm into t. So now we got the time domain equation for the wideband FM. Now we can represent this equation in the frequency spectrum. So the frequency spectrum for wideband FM is given as, at Fc we are having the amplitude as EC into j0 of beta by 2. So in this frequency spectrum we represent both the upper and the lower bands, that is why the amplitude is taken as by 2. and at Fc plus Fm the equation is the amplitude is become Ec into J1 of beta by 2. At Fc plus 2 times Fm the equation is become Ec into J2 of beta by 2. So this sides is varies from minus infinity to infinity. So the spectrum consists of a carrier signal, infinite number of upper and lower sideband frequencies. So theoretically the bandwidth is infinite. So the spacing between the spectral components is equal to the message signal frequency, that is Fm. To the right side of the carrier all the spectral components are positive, and to the left side they are alternatively negative and positive. So the magnitudes of the spectral components depends on the Bessel function value, that is Jn of x. But the Bessel function gradually decreases as n increases. So the magnitude of the higher order frequencies are negligible. So the carrier magnitude in the spectrum varies with the modulation index. The Bessel function coefficient J0 of beta become 0 when beta is equal to 2.4, 5.5, 8.6 or 11.8. So in this diagram the J0 of beta is become 0 for 2.4, 5.5, 8.6, 11.8 for beta values. So for these values of modulation index the carrier magnitude in spectrum becomes 0 and the modulation efficiency reach 100%. So the Bessel function value becomes 0 for beta is equal to 2.4, 5.5, 8.6 and 11.8. So for all values the modulation efficiency is 100%. So here this table represents the different values of the Bessel functions. So the different value of the Bessel functions can be observed from this table, and it can be seen that as we move from the carrier, so as we move away from the carrier the sideband magnitude is decreases and thus it become insignificant. So as we move away from the carrier signal the sideband, that is the higher and lower sideband magnitude become insignificant. So now we can derive the expression for the power calculation for the wideband FM. So the power taken by any signal for an electrical circuit is given by P is equal to V RMS square divided by R. So the carrier signal, so in the spectrum we are having the carrier signal with an amplitude of Ec into J0 of beta by root 2. So the carrier power can be given as Ec into J0 of beta by root 2 the whole square divided by R, where R represents the load resistance. So this equation can be rewrite as Ec square into J0 square of beta divided by 2R. Similarly, the power carried by the side bands can be written as P of Fc plus Fm. So the side band at Fc plus Fm it is given as Ec into J1 of beta divided by root 2 the whole square divided by R, which is equal to Ec square into J1 square of beta divided by 2R. Similarly, at Fc plus F 2 times Fm that sideband power is given as Ec into J2 of beta divided by root 2 the whole square divided by R, which is equal to Ec square J2 square of beta divided by 2R, etc. So at the frequency spectrum we are having infinite side bands, so the power carried by the side bands will also infinite. So the total power carried by the upper sideband sideband frequency is given as EC square into J1 square of beta by 2R plus EC square into J2 square of beta divided by 2R, etc. So, the total power carried by the lower sideband frequency is given as P LSB is equal to EC square into J minus 1 square of beta divided by 2R plus EC square into J minus 2 square of beta divided by 2R plus etc. So, the total power carried by a FM signal is given by the carrier power plus the lower sideband power plus the upper sideband power, which is equal to EC square divided by 2R summation from n is equal to minus infinity to infinity Jn square of beta. So, in both the upper sideband and the lower sideband, the term EC square by 2R is constant. So, that is why the in PT we taken this EC square by 2R is taken outside. So, the PT is now become EC square divided by 2R summation from n is equal to minus infinity to infinity Jn square of beta. So, now we can apply the Bessel function property, that is from summation n is equal to minus infinity to infinity Jn square of x is equal to 1. That is, in this equation this Jn square of beta is equal to 1. So, the total transmitted power is equal to EC square by 2R, where EC represents the amplitude of the carrier signal and R represents the load resistance. So, the total transmitted power in case of wideband FM is equal to EC square divided by 2R, where this EC square by 2R represents the carrier power PC. So, in case of FM, the total transmitted power is equal to the carrier power, which is a constant value. So, now we will derive the expression for the bandwidth using Carson's rule. So, theoretically the bandwidth of FM signal is infinite, because in case of wideband FM it contains infinite number of sidebands. So, theoretically the bandwidth of FM is infinite, but for practical FM the bandwidth of signal should be minimum as possible. So, in communication we have to make sure that the signal bandwidth is minimum as possible as that of channel bandwidth, then only we are able to accommodate more number of signals. Hence, insignificant frequencies must be eliminated from the frequency spectrum of the wideband FM. So, according to the Carson's rule, the beta plus 1 upper and beta plus 1 lower sidebands have the significant magnitudes and contains 99% of the total power. Hence, the FM signal is passed through a band pass filter in order to eliminate the insignificant higher order frequencies. So, from the Bessel function table, it is clear that as we move away from the carrier signal, the higher sidebands signal power is become insignificant. So, according to the Carson rule, the beta plus 1 upper sideband and the lower sideband have the significant magnitude. So, if the FM signal is passed through a band pass filter, we can eliminate the insignificant higher order frequencies. So, according to the Carson's rule, the bandwidth can be written as which is equal to 2 times beta plus 1 FM. So, this 2 times represents both the upper as well as the lower sideband. So, the beta plus 1 upper sideband plus the beta plus 1 lower sideband, which is equal to 2 times beta plus 1 into FM. So, this FM is equal to the modulating signal frequency, where this beta represents the modulation index of the FM, which is equal to delta F by FM. So, the bandwidth is equal to 2 times delta F by FM plus 1 into FM. So, if you rewrite the equation, the bandwidth of an wideband FM is equal to 2 times delta F plus FM. So, this is the practical value for the bandwidth of a wideband FM, which is equal to 2 times delta F plus FM. So, in this lecture we discussed frequency modulation. So, in this module 1 we discussed both amplitude modulation and the frequency modulation, and we derived the expression for the AM waveform and AM modulated waveform and the frequency modulated. So, in this slide we just make a comparison between the AM and FM. So, in case of AM, the total transmitted power is varies with modulation index, that is Pt is equal to the carrier power Pc into 1 plus m square by 2. But in case of frequency modulation, the total transmitted power is constant, that is it is independent of the modulation index beta. So, in case of frequency modulation, the total transmitted power Pt is equal to Ec square by 2R, and the maximum efficiency in case of conventional AM is 33.33%, but in case of frequency modulation the maximum efficiency is 100%. And in case of amplitude modulation, the bandwidth is equal to 2 times FM, that is it is independent of modulation index n. But in case of frequency modulation, the bandwidth is equal to 2 times of beta plus 1 into FM, that is the bandwidth is dependent on the modulation index beta, which is equal to delta F by FM. And the noise effect in case of amplitude modulation, it is comparatively high, because in case of noise we are that amplitude change will be reflected, but in case of frequency modulation the noise effect is comparatively less, and in case of amplitude modulation the circuit complexity is comparatively less, but in case of frequency modulation it is more, and the coverage area is more in case of amplitude modulation, and it is limited for FM, and the frequency reuse is not possible in case of AM, and in case of FM the frequency reuse is possible. So, in this lecture we detailed the concept frequency modulation, then we derived the expression for FM, and based on the value of modulation index beta, there are 2 different types of FM, that is narrowband FM and wideband FM. Thank you.